Hello and welcome to Startup Hack. Today we are going to talk about LinkU speed optimizations. So let's jump right in. Make sure to check out the link down below because we always provide the code samples that you can pull down and follow along so you can see in our project. Do you want to earn $100,000 a year? Do you want to become a software developer within just 3 months? With our amazing course and awesome tutors, you never have to worry about getting stuck. We help students to learn skills that companies want to hire. We are Startup Hack. Don't forget to subscribe our channel. So let's get started. Alright, LinkU is a short for language integrated query. Its name comes from the ability to write queries directly in C#. So here's example. The advantage is that all the query components can be validated by the compiler at compile time instead of having the application fail at runtime. Auto-completion is also supported. So, SharpLab is a great tool to see what the compiler actually does to your code. You can see there that the query is actually converted to something equivalent to this. So here's example. IQueryable is a static class declared in the System.Linq namespace. This means all its methods are static, including the select and where methods used in this query. Note, IQueryable is a huge class with hundreds of methods. It actually a great case for the use of partial keyword. This allows the class to be broken into multiple files. All the methods in IQueryable are actually declared as extension method to IQueryable. This means that the query can be written like this. This makes easier to understand. People is a collection that implements IQueryable person, then where applies a predicted function and return as instance of an object that implements IQueryable, then select applies a selector function and returns an instance of another object that implements IQueryable string. This means that query will keep a reference to the IQueryable string returned by select. The important thing to get here is that LinkU is supported by the methods declared in the IQueryable class. The performance of LinkU is defined by the performance of these methods. Alright, implicit enumerator collapse. LinkU operations are composable, meaning that the output of an operation can be the input of another. We have already seen that a select can be used after where. The implementation of where and select without any optimizations is something similar to here. Each of the operations return an enumerable. This means that to traverse the result of its composition, an instance of each enumerator has to be created. Each item has to be pulled from an enumerator, which pulls the item from another one, which pulls from the source enumerator. Composition of operations is one of the big advantages of using LinkU, but also one of the biggest performance issues. Fortunately, this is avoided in some cases. The use of select after where is a very common usage pattern. To improve performance, the enumerable returned by where has an overloaded for select that returns an enumerable that takes a predicted and selector as a parameters. This equivalent to executing here. It applies both the predicate and the selector in one single for each loop. This means that there's one less layer of enumerators to pull the items, which results in better performance. The same happens if you happen to have two where or two select operations in a row. It would be equivalent to executing one of here. All these enumerator optimizations happen implicitly. You don't need to change anything in your code for them to happen. Okay, now let's move towards explicit enumerator collapse. There are cases where you have to explicitly use a certain overload so that enumerators are collapsed. That's the case for operations like first or default, single or default, last or default, any, and count. All these operations have an overloaded that takes a predicate as parameter. It has exactly the same result as preceding the parameter-less extension
with a where using that same predicate, meaning that source.where predicate count results in the same as source.count predicate, but the second may have better performance. So here's the possible implementations without other optimization for the count operation. So here's the example. The second overload uses one single for each to filter and sum. This saves from using an enumerator to execute the predicate. Alright, source types. All LINQ methods are extension methods for IEnumerable T. So IEnumerable tree is the worst case scenario in terms of performance when traversing a collection. There are several collection types that provide much better performance. The LINQ library assumes that the source collection may have been cast to different types. For example, a list T can be cast to IEnumerable T. By doing this, for example, it is not possible to explicitly call the count property to find how many items it contains. As an example, to find if a collection is empty, we should use any operation. Its implementation without optimizations is here. It has to create an instance of enumerator, then call the method moveNext. If method return true, it means that it contains at least one item. Many collections like list T store internally the number of items. This can usually be retrieved using the length property in the case of arrays and spans, or the property count in other cases. These collections usually implement the interfaces iReadOnly collection T and iCollection T that provide the count property. Calling these properties should be faster than using the enumerator. Alright, value type enumerators. Where uses a custom real list iterator T for the case the source is a list T. This iterator guarantees that the value type enumerator provided by list T is not boxed. On the other hand, all collections provided by .NET do have a value type enumerator, but LINQ doesn't optimize them. As this solution is not generic, it only applies to list T. Also, LINQ doesn't provide any value type enumerator, as all operations that return an enumerable return IEnumerable T, not an explicit enumerator type. Implementation of math operations in .NET has always been challenged, as math operator could not be defined in interfaces. This results in LINQ having to have a specific implementations of sum and average for each numeric type provided by .NET. Unfortunately, .NET 8 makes a faint attempt to use this new feature. It's only using it internally, and it still provides all the overload for the numeric types. This means that third-party numeric types still cannot use the method sum and average efficiently. So here's the example. So thank you for watching this video. The abstractions provided by IEnumerable T makes LINQ a great library so that processing can be easily implemented and maintained. At the same time, it's the biggest cause of lack of performance in .NET applications. So don't forget to subscribe our channel and hit the bell icon for latest updates.
To joining our course, you can simply go to our website called startuphack.com. Thank you.